So we will talk about TCP. How does that change with the wireless? So before we talk about the wireless, we'll talk about TCP, just to review how does TCP work. And the main thing to talk about TCP is the congestion mechanism. Some of you might remember the slow start, but if not, we will just go over that one more time today. Then before that, since we have done quite a bit of work, I mean, I have done particularly quite a bit of work on congestion control. This is my chance to talk about our research on congestion control before wireless and after wireless. And then we talk about and the different solutions on the wireless and satellite networks, which are also part of the wireless. So the whole area of congestion control actually was not known when approximately the time when I got my PhD. So I was hired at Digital, and Digital Equipment Corporation was at that time working on a new network called Ethernet. Actually, it was a Xerox, it was a network that was developed at MIT, went to Xerox Spark, and Xerox Spark had a 3 megabit design, and they wanted to make 10 megabit Ethernet. So they came to Digital and said, why don't we start a fresh design on 10 megabit Ethernet? Actually, they came to, why don't we standardize 3 megabit? And Digital said, no, 3 megabit will not sell. We need to make a 10 megabit. And so we designed 10 megabit Ethernet from scratch, actually. So my group, I was the group that I was part of, actually. I was not having a group myself. I was just starting PhD graduate. So we started working on designing every single piece that you see today in Ethernet. Anyway, one of the things that we wanted to decide at that time was what will happen when we put these Ethernets into the networks of the time, which were mostly 56 kilobit. Most of the lines in those days used to be 56 kilobit. Well, this is new. Okay, so what will happen? And so we put together in the lab a network with some 3 networks actually, as shown here. One which was 1 megabit all the way, one which has a 10 megabit link, and those 2 networks actually. And it turned out that it takes 6 minutes to transfer a file on this network. With Ethernet coming in, it would take 6 hours. So that was just opposite of what we would have thought. If you put a high speed link, the time should go down, if anything, if not go up. And so it went up by a significant amount. And that basically brought us to think about what the problem is. In those days, basically our understanding of the networking was not as good as we have today. This is 1980s, 82, 83 time frame. So that is about 27 years ago. And one of the things that we understood was that if you lose a packet, all you do is retransmit the packet. If you lose 2 packets, all you do is retransmit the 2 packets. If you lose 100 packets, all you do is retransmit 100 packets. And we realized basically as part of this experiment that we started is that really that is not what you should be doing. And so the key realization was that when you lose a packet, it is not just the packet is lost, it's just telling you that the network is congested. It's like if somebody tells you that the Highway 64 is congested, should you be sending 100 more cars because 100 cars are kind of lost over there? If 200 cars are sent, you're not going to send 200 more cars into that one. So the right thing to do if something is congested is to just send 1 car, and when it clears and says, okay, I made it, then you send 2 cars, maybe 3 cars, and 4 cars, and more, up to 100 cars. So so I published several papers at that time. One of the papers, which is very simple in today's term, it was published by IEEE Transactions and Networking, and it said 1-line summary. When you lose a packet, please do not retransmit all of them, transmit just 1. Just 1. That means that if you change your window to 1, you might have window of 100, but if you lose a packet, change your window to 1. So that was the first 1986 publication. Second thing we did was we found out how to go up from 1. So we did something called AIMD principle, additive increase and multiplicative increase, and that has become a classic paper back in 1989. and it has now 1,000 references or so. Then the other thing we did was we also put a bit in the header. We said, okay, why don't we put a bit in the header and we don't have to lose the packet. When the network queues get larger, the network would mark the bit, and then when the bits come back, we know that how much is network is congested. And so that way you don't lose. You don't have to wait for the last of the packet before you can take action. You can reduce the traffic below that. All right. So we had this thing called you decrease to half in the deck bit scheme. You decrease to half. Without the deck bit, we said you have to come down to 1. If you have timeout, you have to come down to 1, and then you go up, multiplicatively, as we said here. Anyway, we made this presentation to IETF in 1986, and Van Jacobson was there in that meeting. He looked at our presentation, he went ahead and then implemented something which he called slow start. So slow start is what is implemented in today, but it has several pieces of our business of timeout and AIMD, as you will see. First of all, what is AIMD? AIMD is additive increase and multiplicative decrease. And the idea is that if you have a window, if somebody has a window of W1 and another user has a window of W2, and the network capacity is some amount, let's say capacity is C, then when W1 is equal to W2, W1 plus W2 equal to C, that is the network capacity line. So this is the line which is W1 plus W2 equal to C. This line means the network is fully loaded. If you are operating below this line, that means the sum is less, and therefore the network is underloaded. If you operate above this line, that means the network is overloaded. All right. Second thing we want to do is we want it to be fair. So if you want to be fair, then W1 should be equal to W2. So if you draw a line W1 equal to W2, that means it is fair. If you operate on this line, then you are fair. If you operate below this line, then you are giving more capacity to W1. If you are operating above this line, you are giving more capacity to W2. So we need a principle to be able to get to this point. So this is the operating point that we want to be on, where it is fully loaded and fully fair. Right, the crossover of the two lines. How do we get there? Well, we said that if you start from any point in this plane, and if you follow additive increase and multiplicative decrease, you will eventually end up at that point. Always end up at that point. And the idea is simple, is that if you start from here, additive increase means both of them add some amount, same amount. So if you add some amount and the W2 adds the same amount, you will be going on along a 45-degree line. Right? So you go up 45 degrees, and then you do multiplicative decrease, means both of them multiply by some number, and so they will be going on a line which is passing through the origin. Right? If you keep doing this, you go 45 degrees and then go through a line which passes through the origin, go 45 degrees, you will eventually end up at that point. Alright, so this is a big discovery at that time. And so the rule is that you always increase by a fixed amount when you want to go up. You always decrease by a factor when you want to go down. So now slow start. Now slow start, what it does is it basically implements some of these ideas in TCP. And the good thing about slow start is that while we were writing papers, this was implemented in TCP, so when you download TCP code from some place, it's already built in. So this was already ready to use. So that's the power of ready to use code. And so anyway, so the way it works is that the sender keeps a window called congestion window. All right, so the receiver gives, the way TCP works is the receiver says, please send me 5 packets. So that is the window of 5. But the receiver sender doesn't send 5 packets. It keeps another window called congestion window, and if that window is 4, it will just send 4 packets. So it will send the minimum of what is allowed by the receiver and what the congestion in the network says. So the CWND is changed up and down depending upon the congestion in the network. and it is counted in integer numbers in the number of segments. A segment is a TCP-PDU, as we call it. A segment is MSS. You see, the thing is, we use the word MSS is the maximum segment size. So that is the TCP maximum packet size, right? So 512 bytes is generally the number. So using that number, you count how much window they have allowed. Because TCP window is, by the way, in bytes. So the receiver does not say that you send me 5 packets. It says, please send me 1500 bytes, right? So you divide that by 512. That will take 3 segments. So you put the receiver window at 3. And congestion window. So the congestion window is 1. You start, whenever you start, you always start with the congestion window of 1. And then you keep up. Every time you get the acknowledgement, you go up by 1. So here is the graph. You start from 1. This is the congestion window, function of time. You start from 1. And when you get 1 acknowledged, you go to 2. And when you get those 2 acknowledged, actually the one acknowledgement will give you the, so you will get 2 acknowledgements, then you go to 4. So what you do is, you increment by 1 per ACK. 1 per ACK is basically, if you have sent 100 packets, how many acknowledgements will you get? 100 acknowledgements in 1 round trip, right? So the number of acknowledgements keeps going up in every round trip. If round trip was time here, you will notice that you get up by 1, then you go up by 2, then you go up by 4, then you go up by 8. So this is exponential increase. All right? And you keep doing this. However, if you never reach the receiver window, or if you reach the receiver window, that's fine. Then you stay at the receiver window. You can never go over the receiver window. However, if you drop the packet any time, if you lose a packet any time, then you bring down the window to 1 again. And you remember where you fell off from. So you fell off from there, so half of that is called SS threshold, slow start threshold. So you remember that number, but you come down to 1, and up to halfway you go up exponentially as before, but after halfway you become more careful, and every round trip you just go up by 1. So this is linear. All right, so here what you do is, here on every acknowledgement you go up by 1, that means every round trip you go up by the amount of the window. Whereas every window here you go up by 1, every round trip you go up by 1, and so this is linear. However, the names are somehow misnamed, and so this is called the congestion, the exponential growth phase is called slow start, and the linear growth phase is called congestion avoidance phase, which is actually better name. That's fine. So the idea is that this is congestion, this is a slow start phase, which is actually a slow start, but it is really going fast in that sense, exponentially up. And then this is called congestion avoidance phase. And if you fall off again, then you remember half of it actually. So this graph is not basically to the right scale, because I would have drawn a line exactly at half, and then you go exponentially up to that half, and then you go linearly. And if there's nothing to send, then obviously you cannot increase the window. So if something is idle, then you just stay, and then when you can start at 1 again if you're idle for a long time. Okay, so that is a slow start. So now we have introduced all the terms that we need, and believe it or not, a slow start has been the most referenced paper in networking, I think, in whole networking. Every year, even today, now paper was published in 1988, every year hundreds and thousands of papers are published in fixing the TCP performance, and every one of them references TCP, slow start. So there are thousands of references to a slow start paper every year. Okay? So this is the most fundamental concept in networking in that sense, most commonly researched and analyzed. Alright, so this whole lecture is actually about that. So we are going to fix TCP for wireless. What are we going to fix? We are going to fix slow start. Other parts of TCP are not analyzed or worried about, but this is the part that is the key. So anyway, in the initial days of slow start, there were lots of modifications suggested, And one of the modifications which got implemented is called fast recovery. And in the fast recovery, they said, and by the way, the TCP implementations, instead of calling version 1, version 2, version 3, they call them by the names of the cities in Nevada. And so the version called TCP Reno is the one that has this modification. Before that was TCP Tahoe, which did not have this modification. So, I mean, those people who work on TCP, or they just somehow remember all these city names. I can't remember all of them, but basically they remember, oh, TCP Tahoe has this, TCP Reno has this, TCP Las Vegas has this, and so on. So TCP Vegas actually has this, and so on and so forth, right? So TCP Reno has this modification where if you get a duplicate ACK, if you get 3 duplicate ACKs, then you retransmit the missing segment, set the SS threshold to half, set the window to half plus 3, and then you go from there. Basically, you don't have to wait until you time out. When you lose a packet, several things happen. When you lose a packet, the receiver is still waiting that hopefully it will show up, right? So let's say packet number 5 is lost. If the receiver gets packet number 6, what does it do? Does it acknowledge anything? Anybody? What will it do? It has gotten everything up to 4, and it acknowledges that, okay, I got up to 4 everything, and I'm waiting for 5. Now it didn't get 5, but it got 6. What should it do? Good point. So what it will do is it will acknowledge 4 again. It will say, I got 4, please send me 5. So you got 2 acknowledgements for 4. That is called a duplicate acknowledgement. Now it gets 7. What will it do? What the receiver will do? Another duplicate acknowledgement. It will say, I got 4, please send me 5. Right? So if you get 3 duplicate acknowledgements, you can be very, very sure that 5 is not going to make it anymore. And that means that you can as well retransmit 5. Otherwise, what previous to this Reno thing they used to do was, the receiver will keep sending this duplicate acknowledgement. At the end, the sender will time out. Sender keeps a timeout timer, says that if I don't get the acknowledgement for 5 within 4 seconds or so, I will send 5. So now acknowledgement for 5 has not come in. So the duplicate acknowledgement had no meaning. Just like before our work, last packet had no meaning. Now with our work, last packet means congestion. So with this work, duplicate acknowledgement means packet loss. Right? So when you get 3 duplicate acknowledgement, you start taking action. The action you take is that you right away send that last packet, but you don't go down to 1. You go down to half. You really come down to this point. And then you go linearly from there. Right? So what you have done is, you have not gone down to 1 and then taken the exponential increase. You have just come down straight to that point. That's fast recovery. You set your threshold to half, set your window to half plus 3, and then on every subsequent duplicate ACK you increase by 1, and so on. Anyway, so this is all about congestion control. But what we didn't distinguish was the congestion and the errors. You can lose a packet because of the congestion. If you lose the packet because of congestion, the best thing you can do is to go down to 1. We told so, right? We told you so. But if you lose because of the errors, it is not the best thing to go down to 1, because you are just wasting your time when it is errors. Errors are not load dependent. Reducing the load does not reduce the errors. Right? And so if you lose a packet because of errors, then you should not change your load. And so that is what is happening in wireless. In wireless, most of the packets lost are not because of congestion. It is mostly because of the errors. All right? So if you have a wireless link where you are losing packets, two things you have to do. First of all, find out whether it is error or congestion. And if it is error, do nothing, just retransmit the packet. If it is congestion, then do one of these slow start things. Right? Now the problem is we cannot do either one because the source is far away from the wireless link. The source could be in Germany, the wireless link is in Washu. Right? The packet is coming on the wired link all the way up to Washu access point, and then it is coming wireless here and it is getting lost. So how does the source know that it's an error or congestion? Right? Source doesn't even know wireless part at all. Now the destination probably is close to wireless most often. Our source could be on the wireless link too. For example, I could be sending wireless, then the last hop is generally wireless. Sometimes middle hops could be wireless, but generally they are the last hops. So there are some networking technologies such as CDMA. In CDMA, yes. In CDMA, code division multiple access, if there is an overload, then that causes more errors. But in most other cases, the errors and the load have no relationship. Okay? So now, first of all, you have to know whether it is CDMA or not, whether it is wireless or not, whether it is CDMA or not, and then whether we should redo anything. So these are the things that have resulted in a lot of research and a lot of papers. So we will talk about 5 categories, and then finally our work on the wireless networks. So obviously we continue on the wireless also. So first, so each of these is a category, in the sense that there are books, full books on this topic called TCP or wireless. All right? And there are hundreds of papers which are published every year. Again, this is a very rich topic, very easy to publish. So what I'm going to do is, actually in one version of the class we followed this book, which is referred at the end of this chapter, which is on the reserve here now. But it is a whole chapter and 60, 70 different techniques it describes. And we could talk about all those 60 techniques, but that gets people to sleep. So what I have done for this particular time is that I have just put one example of each of the 5 techniques. So I will talk about one of the examples of each of these 5. So for example, link layer mechanisms. Actually, this is the whole category. So here we are not going to do anything at the TCP level. We are just going to do at the link level, which is wireless. So on the wireless, we can do very simple thing. First of all, we can introduce forward error correction, FEC. With FEC, we can take care of the errors right there. Most of the errors will be taken care of by forward error correction. Right? So the packet will be delivered, it will be acknowledged on the TCP, and they will not know the difference between wired and wireless. So that is the first thing. Second thing we could do is, at the link level, do the retransmission, ARQ. So for example, on the wired links, we don't do any retransmissions. On Ethernet, when you lose a packet, Ethernet doesn't do any retransmission, it doesn't even have an acknowledgement. Right? It doesn't even have FEC. All it has is an error correcting code, error detecting code, CRC, cyclic redundancy check. And when the receiver receives something on the Ethernet, it checks, and if it is an error, it just throws away, doesn't inform the source, doesn't inform the previous hop, doesn't do anything. Right? So on the wireless link, it is important to do both, the error correction, error detection. And most of the wireless links that are designed, like WiMAX we talked about, they have FEC and ARQ. ARQ is automatic repeat request, which is same thing as retransmission. So those things are required in the wireless. So if you do ARQ, that is a link layer retransmission and acknowledgement. So you have to have acknowledgement for that, because otherwise there is no retransmission. And so when there is no error, there is a slight reduction in throughput, not no reduction. There is a slight reduction in throughput because you have to send the acknowledgement, right? So the acknowledgement do take some bits. Reduced throughput, increased delay at the link layer, but it does reduce. You're right. If there is no errors, then obviously you are not going to do any extra work. Basically, there is no retransmission, but you do have the acknowledgement. If because of that, may cause congestion, and so those acknowledgements may cause congestion. May increase variance of round trip time, and now because if some packet is lost, it has to be retransmitted. The link delay is not fixed anymore; it varies, and that variation may increase the round trip delay of the TCP. By the way, TCP, the way it does the round trip timing is it as the mean, it measures the mean and measures the variance, and uses the sum of the mean and standard deviation, sum multiple of standard deviation. All right, may cause head of line blocking. Now, here's the thing, is that suppose the packets are going to two different destinations. Unless they are properly queued, there are two ways to queue it, that you can make a queue per destination, so you will have multiple queues. If you don't have queue per destination, you have one queue for all the packets going out, then if this packet has not been acknowledged, other packets cannot get out. So that is called head of line blocking. Right? The head of the line has to get out first before the rest of them can get out. So you have to make sure that you somehow take care of that, and then adaptive link layer strategies. Other things you could do is that depending upon the error rate, you could change the FEC code, you could change the retransmission strategy, you could change the frame size. So what do you do with the frame size? If the error rate is high, what you should do with the frame size?
Reduce it.
Reduce it, right, yeah. Because larger packets have higher chances of getting an error, right? Because there is a bit error rate, and if you have 1,000 bits, the probability of error is higher than 100 bits. So the wireless packets in general are very small compared to wired packets, which in general are very large. All right, so these are all the link layer mechanisms. Second thing we could do is split TCP solutions, and there are many of them. I have put 3 other examples that we will not talk about. We will just talk about one of them, which is indirect TCP. The other 3 work very similar, and the reason I put them the other here is that if you ever have to do any research on this topic, then you know what these things are, and you can easily find them. So these are more there for reference, and they are very similar to the one I'm going to talk about, which is indirect TCP. And indirect TCP is a member of a class called split TCP. So what you do is you split the TCP into 2 loops. Generally, TCP is an end-to-end protocol, source and destination, right? So it has a control loop which goes from source to the destination. Packets go from source to the destination, destination sends the acknowledgement, and then, so there is a big loop like that. We break that big loop into 2 small loops. One loop goes to the base station, and the other loop starts from the base station and goes to the mobile host. By this method, there is one TCP here. When the packet is received at the base station, it acknowledges it. The source can then increase the window or decrease the window. So this is the wired part, no problem. And here it does another TCP. The mobile host sends the acknowledgement, and if the acknowledgement doesn't come or timeout happens, something happens, the base station can run another TCP loop, so basically do whatever we do here. This is a shorter loop, and therefore it can sustain more errors without much loss of time. Right? So what we have done is we have broken the big TCP loop into 2 little loops, and what you try to do is you try to keep it transparent or hidden, such that the source thinks they are talking to the destination and the destination thinks they are talking to the source, but in the middle this thing is happening. 2 TCP connections. So now the thing is that in this case, the main thing is that packets have to be buffered at the base station, because they're coming in, they could be coming in very fast here and going out very slow here. And therefore they have to be buffered. And when the sender gets the acknowledgement, they assume that the mobile host has received it, but actually that has not. The base station has received it. And so it violates the TCP's semantics, and there is a state in the base station which is important. Where if the base station crashes, all those packets that have been acknowledged will not make it. Right? Nobody will know that 1,500 packets have been lost with the base station. And also, if the mobile host moves to another base station, we have to move all this state to the new base station, saying, well, here are 1,500 packets, I still got to give it to him. Right? So that is the problem. And does not work if the connection is not bidirectional. So have you seen a unidirectional connection? Yes. So many of you have not seen it, but basically in the original days of satellite communication, there was a service that was offered. You could get the internet by satellite when there was no DSL. So you get the internet basically. So this is actually not that old, but I remember I got this service in 1994 or 95, 15 years ago. So the way it worked is that you go one way on the phone line. So when you want to send a request to the server, you send the request on the phone line. You dial into a modem, send the request. But the modem is very slow. If the server sent you the response on the modem, it will be very slow. So what the server does is, server sends it over the satellite link to your home, which is kind of, it was 480 kilobit, which is faster than the modem, which was 32 or 56 kilobit. So that was the internet, which is unidirectional, or actually it is not symmetrical at least. It is asymmetric loop. On those, this is a problem because, I mean, things are not same kind of round trip. Anyway, this is 95-97 kind of work in direct TCP, and similar things might have continued even today, although I have not kept track of all the wireless TCP work. So this is an example of what we call, what is the class name? Split TCP. And there are other things such as selective repeat protocol, mobile TCP, mobile and transport protocol. All of them follow the same thing. They split it at the base station. The second class is TCP aware link layer protocols. So now, right now, in the layered protocol schemes, we really don't know what is running on the top of me. Right? When you have wireless link, you don't know whether it is TCP or UDP or SRTP, whatever. I mean, there are so many other transport protocols. We don't know that, and we don't care because we have the layered approach. We just work on our layer, right? But with this approach, we have to separate out the TCP packets and handle them differently on the wireless link. And we will use one of the most commonly cited protocol called Snoop. So Snoop protocol, basically you split the connection and the link level retransmission. The base station monitors the returning acts. So the word Snoop means that we really don't send any acknowledgement, but what we do is we look at the acknowledgement as they're going from the mobile host to the source. So there's only one loop, big loop, but the base station looks at the acknowledgements. And what it does is that retransmits on duplicate acts and drops the duplicate act. So it saw that there is acknowledgement where the acknowledgement says, I got 4, please send me 5. And then it says, I got 4, please send me 5 again. So it knows it didn't get 5. It has kept a cache of the previous packets. So it sends 5. Right? The duplicate acknowledgement will not be sent to the source, but will be handled right here at the base. And then the acknowledgement for 5 comes in, then it sends it to the source. So really, I mean, it is just doing all the TCP work. Somehow snooping means hidden way. Right? So advantage is that it is only soft state at the base station. Why it is soft state? Because if the base station crashes, and it doesn't have the packet number 5, no big deal. When the station comes up, it gets the duplicate acknowledgement. It says, sorry, I don't have 5, it sends to the source. Right? Or if the station moves, if the mobile station moves to the new base station, that state does not have to be sent to the new base station, because the new base station will not have a copy of the previously sent packet, and it will just not acknowledge that. It will just handle it as usual. If the wireless link delay is less than 4 packets, 3 duplicate acts will not happen. And so suppose somebody wants to just send 2 packets. Some TCP connection, which is very common, by the way, in web applications. You send a request, you get a response, and done. Right? And if this is only 2 packets, then you get 2 packets. You get the first packet and the second packet gets lost. There is no duplicate acknowledgement as such, because there is nothing to acknowledge. And so what do you do with this thing? So that is a problem. Does not work with encrypted packets. If you have encryption, IPsec, then you don't know what is the transport protocol inside. And so you cannot look at the acknowledgements. Does not work on asymmetric path like we talked about before, and so on and so forth. So this is again 95 work, and one of the class of members which is the member of the TCP aware link layer protocol. So here, even though base station is a layer 2 device, it somehow has a TCP built into it. So the point is, it's not just that if the sequence is less than 4 packets, the last 4 packets probably will not be handled correctly of any sequence, because you will not get duplicate acknowledgements to handle. All right, continuing on, the fourth set of schemes is called explicit notification schemes. So here they modify TCP so that it explicitly says whether this is loss or an error. And one of the examples is right here, ELN. And this works if the mobile host is the source and it is on the wireless link, first half. Doesn't work on the intermediate things. So the base station keeps track of the missing packets from the mobile, and when duplicate ACK is received, BS sets the ELN bit in the duplicate acknowledgement, explicit loss notification. So it kind of remembers that when mobile receives the duplicate with ELN bit set, it does not back off, simply retransmits. Basically, they have a new bit in the header, which is called the ELN bit, and that bit is used to distinguish between the error and the loss. The loss happens in the rest of the network. The errors happen in the first part of the network, and the first part of the network is taken care of by link level retransmissions. The rest of the things actually are taken care of here. So there's a little bit more detail that is missing on this slide. Duplicate acts with ELN bit, it does not back off, simply retransmits. The question is, what happens when there's an error? And the only way I can see is that is handled here. And if all the errors are handled here, then the question is, why do we need the ELN bit? But anyway, the idea is that there is an extra bit which is used to indicate if that bit is 0 in the duplicate ACK, that means it is an error, loss due to error, and if it is 1, that means it is loss due to congestion. And it is assumed that the rest of the network is not wireless, and therefore any loss here in this part is congestion.